Hello, my name is Christian Boyne. This is PHYS 205, the Experiment 6, the lab project. Today is July 24th, 2017. So, as you can see from these equations, today we're going to be working with generators and motors. So, the theory behind how a generator works corresponds to Faraday's law, where we have a changing magnetic flux with time produces a electromotive force, as following this equation. Now, the magnetic flux corresponds to the dot product of the magnetic field and area, BA cos theta, where theta is omega times time, and omega is the angular frequency, or the velocity. So here we have the derivative, time derivative of that following equation. We have a constant magnetic field in an ideal environment, assuming that's an ideal magnet. We have the area, and we have cos's derivative, which becomes sine. So basically what's going to be happening is, as this copper loop rotates, we're going to be experiencing a changing magnetic flux that will generate an electromotive force corresponding to this last equation here, NBA omega sine omega t. If you take this, dividing both sides by r, you are going to then get the current response as seen in this equation. So the current varies sinusoidally with time, and we are going to try to measure that using Logger Pro and a current sensor. The experiment involves just wiring the circuit itself. So using the same setup as the electric motor experiment, a permanent magnet, some connecting wires, DVD covers to elevate, and these paper clips, and some paper clip crimped on so that the electric or the uninsulated copper may sit comfortably on either side, keeps a closed circuit. So I'm also using a current sensor, as we are going to be trying to read the alternating current response off a very simple generator. You want them to be pretty close together so that you can maximize the magnetic field and therefore get the highest current reading as possible. As seen here, a bigger magnetic field corresponds to a higher current. We also chose to make the wire roughly around this size because this provides great stability. If you have too much wire coming out of this and this end, you're going to have an unstable coil that is going to not oscillate as smoothly as this one will when you turn the electric fan on. If you do not have a mini fan such as this, there are little hobby electric motors that can be connected to a 3-volt battery source, such as the D batteries, and hooked up to create the rotation. So once you've wired this side, you clamp here to the paper clip, and then from there to the current sensor. The other side of the current sensor just goes up and to the other side. So it's very simple, easy to set up, and pretty cool because you get a good understanding of how a current response looks. So I'm going to run the electric motor. It will cause this to rotate, and over here I have a current sensor connected to both ends of the copper wire going to my computer. I have a very high data sampling rate. I've set it to 40 samples per second, and I'm hoping to see oscillations in the current. Now, this is a very primitive setup for an experiment like this, so we're going to expect a pretty choppy sine wave that likely will be very hard to get a sinusoidal fit. So now I will demonstrate it being turned on, and I'm going to press start data collection and then turn it on. So over here I have connect points on. We can see that the current is in fact oscillating. The values are so weirdly off, and it is not a constant amplitude because as it rotates, the inertia of this piece of copper wire causes it to lose connection. So we're getting the sinusoidal response, seeing that the current is varying, but we are getting kind of inaccurate readings due to the fact that this disconnects, and I'll talk about that further in the sources of error. Here's the response for the current. varying sinusoidally with time. As discussed before, we had a rather large couple sources of error. The inertia itself of the copper wire is not exactly stable, so it oscillates and throws itself up off of the, let's call them commutators, on either side here and here. So when that happens, we're going to have some current discrepancies, as can be seen. It's pretty reasonable to assume that would be our amplitude, 0.03 for the actual sinusoidal wave, although down here we have a little bit less. This is likely due to the accuracy of the instrument trying to read the values of current at a very high sampling rate, and it's on the order of a little less than milliamps, right? 10 to the negative 4 amps. So that's why it's just a 1 amp difference makes a big difference on this scale of the graph that has tick marks going up by very small increments. So as it oscillates, you can see that what normally should just be up to 0.3, down to 0.3, up to 0.3, down to 0.3, up, down, but instead we have a bit of a different response. And like I said before, that's because it disconnects itself and the circuit then is open and there is no current, and then it reconnects, so then you kind of get this weird from the amplitude down halfway, up a little bit down, and then possibly back up all the way. So bit of a shaky experiment, but it does give you the base idea that you have an alternating current that varies sinusoidally with time when you hook up a generator, or when you make a generator with a coil of wire and a magnet. So that was experiment 6. Thank you for listening to my presentation.